Hello students, in my last video I discussed about pulse width modulation, the theoretical aspect corresponding to pulse width modulation was discussed in the last lecture. In this I will touch upon the practical aspect of pulse width modulation, and here as you can see our kit. So in our kit, the module PWM is here. So this is our core CNA connector pins, CNB, CNC, CND. So these are our pins uh, which allow us to interact with our core. And here you can see the pulse width modulation module. So I can zoom in. So here pulse width modulation, this module. So here is an attached LED. So in our example, for example, we will understand the theoretical aspects of pulse width modulation in greater detail. So here this LED in our example, lab example, here in that example, we have to adjust the brightness of this LED. And the CNB1 is the connector pin which will allow us to connect this module with our core. So along with core, we will see its relation. So as we have already discussed that certain pins are there out of these 100 pins. Some of those pins we can use as an output pulse width modulated pins. So over those pins, we can generate modulated signal, width modulated signal. So once again, we will see those pins which we can use for our pulse width modulated signal. So here you can once again look at the pins. So as we have already discussed, 6 channels are possible. There is only one pulse width modulated modulation module, and in that module 6 parallel channels are possible. So our system can generate 6 parallel single-edged modulated signals or 3 double-edged modulated signals. For double-edge, we require, for single double-edged signal, we require 2 match registers, whereas single match register is fair enough to generate either left aligned or right aligned, depending on whatever the logic we apply to generate that signal. So here you can see the first signal can be taken over on port number 2, pin number 0, that already we have seen. It can also be taken over on the port number 1, pin number 18. Likewise, second channel can be taken over on port number 1, pin number 20, port number 2, pin number 1, and port number 3, pin number 25. So in this way, this process is called multiplexing. And likewise, the third channel can also be taken over on the port 1, pin number 21st, port number 2, pin number 2nd, port number 3, pin number 27, and likewise. In our example, we will use 4th channel, and we will use for 4th channel pin 23rd of port number 1 for our example. It depends on you which pin you will prefer. So suppose if we have to use the channel number 4th and we have zeroed in on the pin number 23rd of port number 1. So we have to configure it as PWM pin, so pulse width modulated pin. we have to configure it. So to configure it, it comes under the function first. So we have to write in the corresponding pin select register. So here it's a port number 1. So port number 1, pin number 23rd. So port number 0 for us, port number 0 we can configure through pin select 0, pin select 1. Port number 1 we can configure through pin select 2 and 3. So here pin select 3 we will use because it's the 23rd pin. Pin select 3 we will use. And likewise, if whatever in our example we are going to use PWM 1.4 and we want to use port 1 pin number 23rd, so we have to configure port number 1 pin number 23rd pin through the corresponding pin select register, that is third pin select third register. 23rd pin we have to select. Now once we have done it, then we will see that how to connect it. Already we have seen one thing that we have to connect C and B1. So C and B1 will provide the connection from PWM module, and over this module we have to provide the signal, the generated signal, which our core will generate. So this is our core. Core will generate the signal over the port number 1, pin number 23rd. Then we have to see that how to connect it. So for that purpose, we have to go to our appendix C in our lab manual, and you can see here very well the port number 1, pin number 23rd is on the pin number 1 of C and B. So connector B, C and B will provide you the connection from your core to your PWM module, where you will provide the modulated signal. So your core will generate the modulated signal over the pin number 1.23, and you can see the description here. So here the function, so this is 00, means if you want to use this pin as GPIO, then P1.23 would corresponds to 00. This function corresponds to 01, and here means not 0, 0, 0, 0, 1 and 1, 0. So over the pin, over the pin number means corresponding to P1.23rd in the pin select third register, you have to write to 1, 0 over that. Likewise, if we want to use 1.5, then it corresponds to 1.24. So in the same pin select register corresponding to the bit position for the pin number 24, we have to write 1, 0. That is all about configuring the pin select register that we will see through a example. Now we will straightway go to our example, what exactly we are doing in this example. So this is example code in which our aim is to regulate or to control the brightness of that LED. So to control the brightness, obviously we want to regulate the average voltage. How you can regulate the average voltage? As we have seen through pulse modulated signal, you have to vary the duty cycle. Duty cycle means you have to vary the pulse width. So here our total cycle duration is 30,000. So that corresponds to 30,000. If you can relate it with my previous example, there we were incrementing our TC only till 6. So here we will increment our TC till 30,000. Now when you were incrementing it 30,000, so that is the total duration. Out of that total duration, for certain duration, you will keep your signal high, and for rest of the duration, you will keep your signal low. So these are all those pulse width, because we have to keep on checking that whether we are increasing the brightness of that LED. So to just realize that thing, we will vary the voltage level. If you will vary the voltage level, the average voltage level, if you will vary, then you can see the change in brightness of that LED. So for that purpose, 10 brightness levels we have taken, and those brightness level we have encoded through these numbers: 0, 3000. So till 3000 the signal will be 1, till 6000 signal will be 1, 9000, 12,000, 15,000, 18,000, 21,000, 24,000, 27,000. For that much duration in terms of ticks or the counter ticks, the voltage will remain high, and for rest of the time the voltage will be 0. Now that is our aim, how we want to do it. How you can do it? So obviously you have to configure the registers. So how we will configure the registers? So we will require the timer function. So we want to introduce certain delay so that we can realize that something is going on. We can understand the transition. We can realize the transition of increasing voltage level through our pulse width modulation. So for that purpose, once you will increment the band the width, after that we will introduce certain delay so that we will become accentuate to the current brightness, and once it will increase, we can figure out the changes, we can realize the changes, we can notice the changes. So for that purpose we have to introduce certain delay. So we will use timer for that purpose. Timer 0 we will use. Hope you can understand the timer function here. So here is the timer function. So I will start with the timer itself. So nothing is there in the timer. We want to introduce certain delay. So to introduce certain delay, we will measure that delay. Suppose 10 millisecond we want to introduce a delay. After 10 millisecond, once again we want to resume back with our operation. So here there is a delay. So we will update our pulse width, and after updation, we will notice the change for a while, and for that while we want to introduce a delay. So here we are calling the delay function delay, and that is for 10,000 milliseconds. So how this function will operate? This function to operate, first you have to decide what is your time resolution. So time resolution means resolution time means after how long will you increase the timer value, the TC value. And how will you do it? For that purpose you have to calculate the PR based on what is your PCLK in relation with CCLK. So here our PCLK is equal to CCLK by 4, I guess. So that is by default. And here we have calculated our PR value. We want that thing to be fixed as 2. 2 means if the value of PR is 2, after 3 cycles of PCLK, we will increment our TC value. So whatever be the duration of one PCLK, so 3 into that duration, after that much time, we will increase our timer value, TC value. Now, same TCR function, you have to enable it. So first you have to reset it. Reset means both your TC and PC value should be 0. What is PC in this case? PC is nothing, but PC is there, which will increment after PR plus 1 cycle delay. And to do that, there is in between one more register. That register is PC register. So PC register will start with 0. After every PCLK, after every peripheral clock, once it ends, it will increment PC. And PC will then match itself against PR value. If both are equal, then PC will become 0, and in the next subsequent cycle, cycle PR plus 1, PC will increment. So that is the importance of PC register. So to do that, you have to reset. So there should not be any value once you will start. So you should reset TC and PC. TC and PC should be 0. So for that purpose, timer 0 TCR value, that should be reset value. So to understand it much better, go and understand the TCR register first. What is there in the TCR register? So TCR register, first value is to enable it, second value is to reset it, and third value corresponding to, means in timer case only two values are used, other are reserved. But in case of our PWM, there is also a TCR register, but there the fourth bit also we will use. Third is reserved, but the fourth we will use to enable the PWM module, that we will see somewhere once we will initialize the PWM. Then you have TCR value. Here you are initially you have reset it, then you are enabling the timer. Enable the timer means now onwards your PC value will start incrementing, and PC value can increment also. That is the importance of enabling it. If you will disable it, nothing will happen to your PC and TC. Now in this loop, you will always check the TC value. You will always check the TC value, whether this TC value is less than whatever you asked for. So here you asked for 10,000 millisecond of delay. So here this 10,000 will be checked, whether the counter value has reached the 10,000 or not. If it is less, so you will always be inside loop. Otherwise, you will come out of the loop and you will just disable it. Now, once you have disabled it, no further increment will happen. And that's all about regarding the body explanation of delay function. So that is about delay. Now we have to initialize the PWM. Already we have seen that how to initialize the PWM module. So obviously there also we have to configure, or we have to write some values in the registers corresponding to PWM. Already I have discussed those registers with you. First and the foremost thing is we have to configure the pins. Here in this example, we want to use PWM 1.4. So fourth channel we want to use. So fourth channel we want to use over. We want to take over that signal over pin 23rd of the port number 1. So port number 1 dot 23rd we have to configure as PWM pin. How we can configure? What we have to write for that purpose? Already I have disclosed that thing, that what we have to write for that. Here 1.23rd. So this is the third function. So zeroth function, first function, second function. So we have to write corresponding to the bit position for 23rd pin in pin select third register as 10, because 00, 01 and 10. Second two value we have to write. So here exactly the same thing we are doing. So here in the initialize pin select third register, and if you will convert it, it would amount to configure the bit position corresponding to 23rd pin as 10 function 2. Okay. Now once you have done it, second thing what will you do? So now your pin is ready. So pin you have already configured as PWM pin. Second thing what will you do? Second thing is that you have to enable PWM. So you have to enable. How you can enable PWM? There is a PCR register. So once again, see what is there in the PCR register. PCR register. So PCR register to by default we will keep those things as single edged. We don't want the double edge or centrally aligned PWM, because to deal with centrally aligned, then we require for single signal to generate, we require two match registers. We don't want to complicate that that much. And to keep the thing simple, we will keep 2 to 6 as zeros. So we want to single edge over that pin. But here from 9 to 14, 9 corresponds to channel number 1, 10 corresponds to channel number 2, 11 correspond to channel number 3, uh, 12 correspond to channel number 4. So 12th bit, so 12th position bit should be 1. Exactly, I mean, it's not 1, that should be, that should be 1 to enable it. Yes, it is to enable. So to enable it, that position should be 1. So how exactly are we doing this? So here, PCR register. So this bit we have made it as 1. That's 14th, I think 12th bit. So 1, 2, 3. So till here 11, and the 12th bit is 1. So that make means this way we have configured our PCR register. So through PCR registers, what you need to configure, either you can configure it as a single edge or double edged, or you can configure or you can enable. Second possibility is that to enable the corresponding channel, you have to do that. So by default, it is single edged for us because the value is 0. Now our PR value is 0. PR value corresponding to our thing is 0. What is the PR value? So you have 3 registers: PR value, PR register, then you have PC register and TC register. Time counter register will increment after PR plus 1 cycle. So here the PR is 0. So after every clock cycle, your TC value will increment. That is the significance of writing PR value as 0. So making PR value is equal to 0 just mean that after every increment, after every clock cycle, your TC will increment. Then this is MR0. Already we have discussed, we have 7 match registers. Out of those 7 match registers, from MR1 till MR6, we will use corresponding to channels. So those MR registers will hold the duty cycle values. So pulse width, whatever be the width of that pulse, that width those match registers will hold. Apart from that, there is a spatial register MR0. That register will hold the total duration. That register will hold the total duration for which signal will be high plus signal will be low. So that will hold the total duration. So here the value is 30,000. Out of that, some time for 0 duration signal will be high. For some time, 3000 ticks till 3000 ticks. So till TC will become 3000, the value will be high. Then till 6000, value will be high. In this way. So there are 10 different values. Then once it is done, then obviously what will you do after matching? So there are 3 possibilities corresponding to every match. So starting from MR0 till MR6, there are 3 possibilities. So you require an MCR register 21-bit positions. Initial first 3 corresponds to MR0, subsequent 3 corresponds to MR1, and so on. So there are 3 possibilities. First possibility is interrupt. Second possibility is reset the value TC and PC, and third possibility is stop it, whatever be the value, so keep it as it is. So here we will reset it. So once your MR0 matches with the TC value, what you should do? Obviously you should restart. So you will reset it. So this corresponds to LPC PWM MCR 1, because the first position should be 1 to reset it. Then already I have explained in my last lecture what is the importance of LER. So LER is related to shadow registers. So once the comparison will start, so comparison will start on shadow registers. You have values in your match registers, but match register first latch that value to the shadow register. So every match register has its own shadow copy, shadow registers. So shadow register will just hold the value whatever in the match register. But if you want to revise the value in the match register, you have to relatch it the shadow register. Then only the revision has a significance. So to do that, so in LER register, you have to write the value corresponding to that match register. So you have 7 match registers, so 7 match registers. So here in general, what they have done, they have made all the 7 registers value, 7 match registers value as 1. So that whenever you want to revise the value, that would be possible. Then here in the TCR register, so TCR corresponds to, means it's a time control register. So first position corresponds to enable it. Second position corresponds to reset it. So here I guess I think we are resetting TC and PC. In the next one also we are doing the TCR, that is to enable PWM. So the fourth position, so here I think 9 means 1000. So fourth position we are making as 1, that corresponds to enabling the PWM module. In I guess uh, these two statements you can also club. So how you can club it? Second position should be 1 and the fourth position should be 1. So in that way you can write some other value. What value you can write? To second 0 0 1 0, that is 10A. So 1010. That value you can directly write. Now that's it. Now we will go in our main function what exactly we are doing. So these are the pulse width. So these are those values which will keep on changing. That is, so you may relate it with the duty cycles. So first time the duty cycle would be some percentage. Second time we will increase our duty cycle. Third time we will increase more, then more, then more, and then more until 27,000 ticks we will go. So that is that width for how long your signal will be one. Then these are the count, total pulse width count. So initially the count is 1. Okay. So direction is 0. So direction, I will later on explain this, what exactly they are doing. Now here we are initializing our PWM. So initially when you are going inside your main loop, you will initialize. Obviously you have to initialize your PWM module as with any peripheral. As we have seen the initialization of those peripherals. Initialization means nothing. It is just configuring those registers. So if we know the PWM registers, those registers we have to configure. So once you are inside it, so we have already seen, so that pin we have to configure, and PCR, PR, MR0, MCR, LER, TCR, and this TCR. So these two things you can club. So that is all about initialization. Once you have initialized it, then you will go inside while loop. Then always you will go inside that never ending while loop. So here you will keep on incrementing your pulse width. Okay. Now you will keep on incrementing your pulse width. So initially the count is 1. So you will go to 3000. Then you will introduce certain delay. If the count is equal to num place this, I mean it is just that this piece of code is just to keep you inside the while loop and to keep on changing these values from 0 to 27,000 and then back from 0 to 27,000. So for that purpose, so we have written this piece of code because we want to keep on changing our pulse width. So here when you are calling the update pulse width, what exactly you are doing? Here in update pulse width, what exactly we mean to do, we want to change our match register. So which match register we are using? We are using 1.4, PMW 1.4. So match register 4 we want to use. So in update pulse width, so pulse width modulation 1, there is only one module. So dereferencing MR4. So MR4 register we have to update. If you will update this MR4 register, already this updation will affect because already you have done this LER initially. So once you have done it, later on also you have to done it. You have to do it. If you will not do it, then shadow registers will not take the value. So for that purpose, you have to always write after updation this value, so that later on in the next cycle, updation, whatever you have updated, that value will be latched to what? To shadow register, because all comparisons will take place, will hold only on shadow registers, not directly on match registers. So first you will write on the match registers, and to latch that value, whatever be in the match register, to latch that value to its corresponding shadow register, that value should be 1. So here in general, they have made all initial 8 bits as 1. So obviously corresponding to the 4th bit position also, the value will be 1. So that is all about this program. So this program will then generate the modulated signal, the width modulated signal over the pin 1.23, port number 1, pin number 23. And to now in the second program, we will adjust the brightness of the same LED, but we will regulate that thing through our keypad. So I want to show you keypad. So here is our keypad. So here you can see the keypad. So this is our keypad. Through this, we want to regulate our brightness. So for that purpose, our idea is to use the first row. So once you press this switch, the brightness level should be somewhat. Once you will switch it, the brightness level should increase or decrease depending on whatever the value, that match register value you will choose. And likewise, when you will press the switch this, the value should be different, the brightness should be different, and this. So we have to only use these 4 switches of our first row, or to say row 0. Row 0 and all 4 columns we have to use. Now, first we have to see that how many pins do we require. So first we have to realize that to actually attempt this problem, first we have to figure out that how many pins do we require. So 1 pin we require for our output signal, that is PWM, for PWM operation. So in this example also we will use the same port first and pin number 23 as our signal pin, output signal pin. But apart from that, we want to use these switches. So 1, 2, 3, 4, 4 columns and 1 row. So we require how many pins? 5 pins. 4 pins. Now it depends on you, how will you approach the problem. So these 4 pins, row can be connected to 1 pin. That row we will use as input. We'll capture it. We'll see whether the value is 1 or not. And these 4 columns, we will attach to 4 different pins as output pins. Those output pins will keep on varying. First, corresponding to this output pin, we will make the value 1. Then in the same loop, in the same for loop, then once again we will make this as 1. At a time, only 1 column we will make as 1. So the moment, like suppose if corresponding to column number 3 in the loop, the value is 1, and at that same time you have pressed this switch, and at the same time the row value will be 1. So if your row is 1, then we will check the corresponding column number which we have, because that is in our hand, that is inside our loop. We can just that, and we will keep on monitoring our row value. The moment the row value will become 1, then we will notice what is our column value. Depending on these two values, we can easily judge which switch we have pressed. Depending on whatever the switch we have pressed, one particular value we will assign to our MR4. So same register we are using. So we will update our MR4. The moment you will update, next step is you have to enable it through LER, so that whatever the value you have written in match register 4, that value would find its reflection, and the shadow register would find its copy. So that's exactly we have to do, nothing so difficult. If you can understand the keypad better, if you have understood the keypad, if the concept is clear, then it is simple. So it's exactly the same program. So I don't want you to further elaborate on, and I don't want to elaborate further on how to make input and output, how to make any pin as GPIO, which pin will you use. So you can go through the program, you can easily understand. My point is, if whatever the value, that value is, so this is the encoded value. So if you have gone through the keypad program, you can easily relate it with and already I think once we have asked the same problem in assignment also, where 4 initial columns means first row you have to only judge. So on that line also you can think, if you know the answer to that problem. Now, if it is so, then update pulse bandwidth. So this is one value, this value you can change. So here it is 25% duty cycle. Next time, if the temp value is 2, so if you have pressed the second column, then duty cycle is 50%. So update it, and 75%. I mean, if temp is 4. So first is 0, second 4, and 8. So in this way, you can update it. So depending on the keys, which key will you press after judging that key, so you will call the update pulse bandwidth with proper argument. Otherwise, every function remains same. It is that simple. And I hope you can understand this problem and the solution better once you will go through this program once again, because I don't want to focus too much on this program, because it is just an extension uh, of the previous program where already I have given enough information on each function in detail. Here, the extra part is just how you will integrate the keypad. If you could easily integrate it, the logic depends on you, that how would you do it, how many pins you will use. So the entire logic depends on you, that how will you approach the problem. I have mentioned that only one row is there, 4 columns. So we require one pin corresponding to row as input pin that we will keep on monitoring. The moment the value is 1, then we will figure out what is our column value. At a time, only one column value will be there. If the column value is any column value, so then we are judging the column value. So this if condition is based on the column value. So this if condition is based on the column value. So if temp is equal to 1, so your first value is so you are using 4 columns. So 0th column, first column, second column, third column. So if the first is 1, that means temp value will be 1. If the second column will be 1, then the value will be 2. If the third column will be 1, then the value will be 4. If the fourth column will be 1, then the value will be 8. So in any way you can judge it, this if condition. You can make your own code for that matter. I hope this would be interesting for you, and you will carry forward with another problems too. See you in next lecture.